accommodation, enjoy the Yoho living experience in addition to the convenience of being right next to the university. Yoho stands for much more than just hostels. It provides safe and comfortable environs both inside and outside the rooms. 850 kilowatt solar power machines are installed on the university terrace area for using sunlight for as many activities as it can. It has been awarded with the Lead Indian Platinum Award for Energy Conservation and Environment Design. The event calendar provides for plethora of music, dance art and festivities that there is an aura of celebrations around the campus. The university holds special annual fests, annual day celebration wherein students can enjoy the different cultural activities and showcase their talent. The farewell party for the students is also organized by the university to bid them warm goodbye and wishes. Manipal University, Jaipur is synonymous with excellence in higher education. It thrives to sum up the vast ocean of knowledge and provide an experience to the students where education is celebration.
Where is it? मैं लाइट बंद कर रहा हूँ, ठीक है? आप चेक करिए।
In Manipal University, Jaipur, exposure is being provided to every single student, and faculty make sure that students work on their weaknesses. All the faculties, including HODs, deans, and directors, are easily approachable. And this was the main reason that I had also done my masters in mathematics from Department of Mathematics and Statistics. I will also be pursuing my PhD from the same department. Every year, placement drive is being conducted by renowned companies for students of BSc and MSc, and they make sure that students get placed according to their caliber. At the end, I would like to thank all my faculties, including HOD, Dean, and Director, for bringing a positive change in my personality and being supportive throughout the journey of Manipal. Thank you.
My name is Dipya Chandranani. I have done my bachelor's in mathematics honors from Manipal University, Jaipur. The faculty here is very calm and cooperative, thus providing students with a very warm environment. The course structure is well designed. The labs are very good with the latest updated softwares. MUJ also has a placement cell. I got placed in Capgemini. Overall, I can say MUJ is good in every aspect. Thank you.
Uh, Good afternoon, everyone. So, I welcome you all to the second day of our 5 days workshop. So, I hope you really enjoyed the studies, lectures, and sessions and discussions. And I would like to inform you that due to some technical errors, our second speaker is like being late. So, we will update maybe he will join in maybe 5 and 10 minutes. So, we are really sorry for that. So let me inform you that our speaker has joined the meeting. So we'll be starting in a while. So thank you for your cooperation.
Okay. Dear participants, very good afternoon to all of you. On behalf of the Department of Mathematics and Statistics, Manipal University, Jaipur, I, Dr. Mahesh Kumar Dubey, welcome you all again to the second day of this international online workshop. I hope you had really enjoyed this study lectures and discussion. Today, we will be having two invited talks from eminent personalities. Once again, I kindly request to all the participants to mute your videos and audios. If you have any questions during the presentation, please type them in the conversation chat box. I will bring them up to the speaker after each presentation and we will have a short discussion. Now allow me to introduce our first speaker of the day, Professor Snasish Chakravarti. Professor Snasish Chakravarti has been a dedicated higher administration grade professor and researcher at the Department of Mathematics, Applied Mathematics Group at the National Institute of Technology, Rourkela, India. He is the author of more than 20 books and 430 research papers in national and international reputed journals and conferences to till date. His research interests include mathematical modeling, machine intelligence, uncertainty modeling, numerical analysis, and differential equations. Professor Snasi Chakravarti obtained his PhD in mathematics and MPhil in computer application from IIT Roorkee. Professor Chakravarti did his postdoctoral research at the Institute of Sound and Vibration Research, University of Southampton, United Kingdom, and at the Faculty of Engineering and Computer Science, Concordia University, Canada. He was also a visiting professor at Concordia at McGill University, Canada, and visiting professor at the University of Johannesburg, South Africa. Professor Chakravarti is also a recipient of various awards like the University Gold Medalist for MSc and MPhil, the Indian Science Congress Association Platinum Jubilee Lecture Award, CSIR Young Scientist Award, Coast INSA International Bilateral Exchange Award, etc., to name a few among others. Preliminaries, his research focused on the applications of numerical modeling to a broad range of problems, the essence of which has been widely published in both books and peer-reviewed journals. So far, he has guided 12 PhD candidates. Now, without further delay, I would like to hand over the session to Professor S. Chakravarti. Welcome, sir.
Yeah, thank you very much. First of all, very good afternoon to all of you. Can you hear me?
Yes, sir, you are audible.
Yeah. So anyway, it's a great opportunity to meet with all of you, although virtually. But anyway, I hope
Hello. Sorry, sir. Just you have to unmute your voice, sir. You have to unmute your mic, sir.
You are muted, sir.
so you can you hear?
Yes, sir. Now.
So that okay. Anyway, so again I have to repeat, I think.
Yes, sir.
Anyway, so very good afternoon to all of you. It is a great opportunity to meet with all of you virtually in this difficult situation of COVID-19 pandemic. So anyway, this is the only way to meet now. So I hope that we'll have fruitful discussions with this lecture. Although he has introduced many things about me, but those are just nothing. But just he has done his duty, no problem. But anyway, no need of all this. Anyway, let us start the lecture directly without taking much time. So I am sharing my slides just to see whether it is visible. Okay. So is it visible?
Visible. Yes, sir. It is visible.
Okay. Okay, so can I start now?
Yes, sir.
Yeah, hello?
Yes, sir. Yes, sir.
Okay. So the title at which is shown, this title is Fuzzy Differential Equations and Applications. So before, actually, I don't know how many in this means audience they know about the fuzzy set theory and interval computations, etc., etc. So I will start with some basics. Then I will go to the differential equation, ODEs, then little bit about PDEs, then some application problems. So with this, let us see. So we know that any engineering or practical problems, with those actually may be modeled with respect to different differential equations, system of equations, eigenvalue problems, depending upon the model of the system. And we have the structures, diffusion problems, biological, medical problems, everywhere we may have the solution of, we may need the solution of differential equations. Suppose we want to use the finite element method, for suppose structural dynamics or any other fluid problems like that. So if it is static equation, static state or static problem, so we lead to simultaneous equations, maybe linear or non-linear. If it is dynamic state or the dynamic problems will lead to eigenvalue problems and so on. Okay, so till now what the people has done, although solve all these problems using the crisp values of the parameters or material properties, initial conditions, boundary conditions, etc. But actually in practical sense, whenever we have some, suppose some measurement or something, we are doing some measuring or observing something, so there must be some error. So then those errors lead to some bounds, and those we may call as uncertain bounds. But again, if it is uncertain, we have three types of uncertainty, that is probabilistic, interval or fuzzy. So these three I will discuss later, means when to use interval, fuzzy or probabilistic analysis. So before that, let us see what is fuzzy set theory. It is actually a branch of artificial intelligence or soft computing. In soft computing, we have different types of techniques, namely artificial neural network, genetic algorithm, fuzzy, support vector machines, swarm optimization, etc., etc. And we do have also hybrid methods. Means we can use suppose GA and ANN, fuzzy and ANN. So if we use different
Sorry,
soft
sir.
computing techniques,
Excuse me, sir.
and we yes.
Sir, excuse me, sir. Sorry, sir, to interrupt you.
Yeah.
Just make it the slides in full screen. Actually, almost 400 participants are on. Now, Professor.
This is
Actually,
okay?
some participants are on the live event.
This is
Oh,
okay?
yes, sir. Perfect, sir.
Okay.
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 Thank you, sir.
No problem. Yeah. So, and the problems with respect to these are prediction, classification, pattern recognition, etc., etc. So now, what is actually crisp versus fuzzy? Crisp, we know in the case we have the two answers, means either it is a true or false. Suppose I tell that man is strong or weak. So answer may be man is strong or man is weak. But what about if it is very strong, or it is very weak, etc. Means I may not have then the solution or the answer as true or false. That means I don't have the two answers. I may have a set of different answers with some probability or means some membership or something. Similarly, if I have temperature is hot or cold. What about if it is very cold, very cold, very hot? How we can define? So that is why we may have answers uh, yes or no, and including the in-between answers, partially yes, partially no. So those are actually we can handle with fuzzy. Again, I told that probability also, it handles the uncertainty, but this probability we need plenty of data. But usually means see when we have some costly experiment or etc., we may not have the means plenty of data. Or suppose it is time consuming, we may not have plenty of data. Then we may go to interval or fuzzy. Okay, so actually this fuzzy set theory, actually first notion of this theory has been given by Professor L.A. Jade. So, so with this, now you see, if we have the physical systems, I already told that if the physical system we develop a mathematical model, in general, we may have it is ODE or PDE, that means ordinary differential equation or partial differential equation. So with this, so in those differential equations, we have different parameters and variables. So these parameters and variables are coming from actually from nature. So if it is from nature, so then we consider this as crisp or exact, or we may have uncertain. So if these are crisp or exact, so any numerical or analytical methods, we know people are solving these problems by plenty of methods throughout the world. Now the problem is if those parameters and variables are uncertain, then uncertain means we may have vague, imprecise or incomplete information of those parameters or variables. So then we have three choices. First one is probabilistic, second is interval analysis, third one is fuzzy theory. So now if it is probabilistic, so those then we should have some random variables, some probability density function, and we know that for those we need plenty of data. So if you have plenty or sufficient data, no problem, you can go to the stochastic or random ness of the parameters and all those. If we don't have the sufficient data, then we may have two options, that is interval analysis or fuzzy set theory. So now, so from here, then from interval analysis, we can have actually the problem we can solve. And if it is suppose fuzzy theory, then fuzzy set theory can be converted to means using that alpha cut into interval. So finally, what you see, I will have actually now the, if you see, fuzzy or interval differential equation. So this is the philosophy behind this, why we need this research field, that is fuzzy or interval differential equations. So this is the father of fuzzy. He is no more, but he gave the notion of fuzzy sets, the fuzzy set theory in 1965, and the fuzzy logic in 1973. So crispness and impreciseness. So this I will skip. I already discussed. So if you see the classical set and fuzzy set, in classical set, the membership function or membership is either 0, 1 or 1. That means it will only include or not include. Suppose X in A, set A, or X is not in A. But in fuzzy set, if you see, this membership is in a closed interval 0 and 1. So in between we have various values of 0 0.1, 0 0.2, 0 0.3, etc., depending upon the problem, depending upon the user. So I will go now directly. So now the same thing, same flow chart I am showing. So if we have system of linear equations, then all these will come, and so we'll convert, or we may have fuzzy or interval system of linear equations. Ax is equal to b with tilde. So this tilde actually designate the interval or fuzziness of the system. And similarly, if I have eigenvalue problem, so I have the eigenvalue problem Ax equal to lambda Bx. We know how to solve this when it is not fuzzy. So if it is fuzzy or interval, we will have this Ax equal to lambda Bx with all tilde, where all those are fuzzy or interval. Then we need to develop methods, or need to have the methods to solve those problems. So those who don't know the may not know the fuzzy set. So that's just I'm giving the definition. A fuzzy set U tilde on the real line R is defined as the set of ordered pairs such that U tilde is equal to X, comma mu U tilde X, where this mu tilde X is called the membership function, and this belongs to 0, 1. Close set. From here we define fuzzy number. A fuzzy number is a fuzzy set which is convex, normalized, and it should be fuzzy set such that we'll have this mu ux such that R to 0, 1 for all x belongs to R. So this is the definition of fuzzy number. So this should be piecewise continuous, this membership function. Now for a particular fuzzy number, suppose there are various types of fuzzy numbers, triangular, trapezoidal, Gaussian, etc. Just I'm showing you the triangular fuzzy number. So next slide I will show the triangular fuzzy number. This is we define by U tilde equal to A, B, C. So if you see here, this is your A, left side A, B in between, and C is right side. So we define the membership function like this: mu U tilde x is equal to 0 for x less than equal to A. So if x less than equal to A, this function is 0. And if from A to B, so it is x minus A by B minus A. And if it is B to C, it is C minus X by C minus B. And after that C, it is 0. So this way we define the membership function for a triangular fuzzy number. Similarly, we may have trapezoidal fuzzy number, we may have Gaussian fuzzy number, bell-shaped fuzzy number. There are a variety of fuzzy numbers. So if you see now, these are just showing how from A to B, these are the functions. Anyway, so from this TFN or the triangular fuzzy number, I can have alpha cut representation. Alpha cut representation is nothing but we convert, we transform this to interval form using this alpha. Okay, with alpha belongs to 0, 1. So you see U tilde can be written as interval U lower and U upper with that alpha. One minute, it's not going. we have the fuzzy arithmetic, because if you want to solve any problem, linear system, eigenvalue problem or differential equation, we need to have different addition, subtraction, multiplication, division. So here we are just writing those operations. If I have two fuzzy numbers, so fuzzy numbers can be converted to interval form using alpha cut, where you see alpha is there. So x lower and x upper with alpha. Similarly, y is another fuzzy number, means with in terms of alpha cut. So if x tilde equal to y tilde, if and only if x lower is equal to y lower and x upper is equal to y upper. Similarly, addition, subtraction, multiplication, division, all I can define. If you see, suppose this multiplication x tilde into y tilde, minimum of s and maximum of s. What is S? S is the combination of all those multiplications, possible multiplications. You take the left side, the minimum one, and right side, the maximum one. So this is the way we do actually the computations. Suppose, so for interval also I can write, for alpha is not there, same procedure, addition, subtraction, multiplication and division. And remember this B1, B2, etc. should not be 0. Otherwise it may not be defined. See, these are the some preliminaries of interval, means some definitions. Interval center, AC is defined as A upper plus A lower by 2, interval width, interval radius, and interval matrix. This is important. I may use this interval matrix. AI is equal to A lower and comma A upper. Here, that means each of the element of the matrix are in the form of interval, having lower and upper. So that means we have not this values, we have the interval values of all the elements of these matrix elements. So it will be a little bit complicated to solve for any linear system or eigenvalue problems. Similarly, okay, so just I'm giving one example how complications may come. So suppose I want to solve a very simple problem, 2, 3, x lower, x upper is equal to 6, 10. So if I use the interval computation, let us first multiply, because these are all greater than zeros. So there may be complication if it is less than 0, etc. also. That I am not discussing because time limitation is there. So suppose this is positive, 2 and 3 are positive. So I can multiply this positive 2x lower and 3x upper. So then left and right, I will compare from both sides. I can write 2x lower equal to 6. So x lower is equal to 3. Similarly, 3x upper equal to 10. So x upper equal to 10 by 3. The solution is x lower, x upper is equal to 3, 10 by 3. Now, if I do this problem in this different way, so what we are getting? You see, x lower, x upper. Now I am dividing this. Means taking 2, 3, that other side, right hand side. 6, 10 into 1 by 2, 3. So we know from the definition of division that we write this 1 by 3 into 1 by 2. Then multiply and you see the result is different. So you see there are many fallacy, many you have to understand that there are many definitions of this, these computations and all set theory. So we have to keep track of those, which one to take, means depending upon the requirement and all. So we have, if you means solve this by different other methods or other combinations, you may have other solution. So this is a simple one variable system. You are seeing how complication we may come, and so that is why if it is linear system of equations having 50 by 50 matrix or eigenvalue problem 50 by 50, then we may have problem. Similarly, okay. So now I will come. Actually, we have done many problems. Actually, see this. Whatever I am presenting, all are done by my PhD students. They have worked, and they're actually those actually I am presenting. So I should give thanks to them. Anyway, so this is your interval differential equation and fuzzy differential equation. So this we have done. And we know that this, when we solve these equations or eigenvalue problems, those actually this is problem dependent. We may not have a general method to solve those problems. We may have weak solution. Weak solution means after multiplication, division, etc. inside that, we may have the left side as large value and right side as low value, means minimum. Means we can have the improper intervals, not the proper intervals. Similarly, I can have incorrect inner or outer approximation. Then you can see interval and fuzzy arithmetic if I write. So till now, this inverse of an interval matrix is an open problem. Till now, nobody has given a correct or good method to find the interval, means the inverse of an interval matrix. People have done, but with some assumptions. And sometimes those assumptions are not correct also. Moreover, you have seen that subtraction and division, we have problem. In division, I told that B1, B2 should not be 0. Or if it should not be very, very less. So then we may have problem. In subtraction also, if you see A minus A, it may not be 0 in interval. Okay, so now two things I will define, and those two definitions I will use in my problems. First one is single parametric form of fuzzy number, and second one is double parametric form of fuzzy number. So I define an arbitrary triangular fuzzy number U tilde is equal to ABC. I have already defined this triangular fuzzy number, what is A, what is B, what is C. So through, now I have changed little bit, in place of lambda I have taken R, this is lambda cut. So here I am using R cut, means lambda cut. Through R cut approach, where R belongs to 0, 1, this can be represented as, I already told that this is alpha cut. So U tilde as B minus AR plus A, comma, minus C minus BR plus C, sorry. So if you see, if I put R is equal to 0 here, so what I will get? I will get A, comma C. Okay, that means left and right. If I put 1, so what will get? Only B. Okay, so in this way, different values of R I can put, and I can have the different solutions for the particular problem. So this is your single parametric form. This is your double parametric form of fuzzy number, where what we have done now, R form you have in the previous slide. I have introduced another, we have introduced another parameter beta, and we write this U R beta, U tilde R beta as beta into U upper R minus U lower R plus U lower R. So again, beta belongs to 0, 1. So this way we can convert each TFN to double parametric form, and you see that this R and beta, these are two parameters we may control, that may control the uncertainty of the problem. Put different values of R beta, you may get the fuzzy solution or interval solution depending upon the values of R and beta. So see, we have actually proposed a number of methods. I'm not going to detail all these methods. So these are the analytical methods for fuzzy ordinary differential equations. So first one is using fuzzy center. So see, these are all available, open available now. You can go to my Google Scholar citations, Google Scholar site, and you can download my papers from there. So you can have these methods also, but one I will discuss here. So this using fuzzy center, using addition and subtraction of fuzzy numbers, using fuzzy center with fuzzy radius, and the fourth one using double parametric form of fuzzy numbers. So this one I am going to discuss now in the next problem, that is method 4. So see, method 4, let us consider an nth order fuzzy differential equation. So this is 3.1, or this equation is your nth order fuzzy differential equation, where I have used tilde. I already told tilde I am designating for fuzzy. So why tilde? Why tilde? This n means upper suffix n means nth derivative, and where AIT, these are continuous on some intervals, subject to fuzzy initial conditions. Here what I have taken the initial condition only as fuzzy. So I have y tilde at t equal to 0 as b0 tilde, y dash tilde 0 is equal to b1 tilde, like that. So I have b0 tilde, b1 tilde up to bn minus 1 tilde, all are fuzzy. Here bi tilde are fuzzy numbers. So if we want to solve this, I already told, see, this through R-cut approach, those yi I can write in terms of R-cut approach. I can write in R form. So the same equation I can write in TR form, subject to fuzzy initial conditions. So initial conditions also I can write in terms of, there are little bit computations, means that those I am not showing all details. So these are lower and upper, all initial conditions. Now next is I will use the double parameter, means that parameter beta. So if I use parameter beta, so you see now beta is coming here. So in this equation, and again in the initial condition also these betas are coming, where R and beta belongs to 0 and 1. So this fuzzy equation means a differential equation and corresponding initial condition have been transformed to R beta parametric form. So R beta parametric form, so just we have supposed this term as y tilde j, and after substituting these things, we may have this equation like this. It is simpler to see. You see this equation, y tilde n t comma r comma beta plus n minus 1 t y tilde n minus 1 t r beta, etc., etc. So I have here r and beta with t. Okay, with fuzzy initial condition, again here you have the r and beta. So we can solve directly with for particular values of r and beta. So then to obtain the solution bound in single parametric form, if we put beta equal to 0 and 1, if you see beta equal to 0, if I put, the solution will come for y lower tr. And if I put beta equal to 1, I can have y upper, y tilde tr comma 1 y upper. So lower and upper I can have the solution in terms of interval. So let us take a very simple second order ordinary differential equation from electrical circuit that BTech first year used to do, or 11, 12 class. So it is second order ordinary differential equation where you see q tilde 0 and q dash tilde 0 are given in terms of fuzzy, where R actually controls the fuzzy set. You can put R in any value between 0 and 1. You can have the interval form of these initial conditions. I have considered this as a general initial condition because this Buckley 2001, he had solved this equation using his own analytical method, and he has given the solution, exact solution like this. So now I will apply this problem using our double parametric method, and you see that the same solution we can get. So see here, if I introduce that same R beta, I have already discussed about how to introduce that. So this is the equation after introducing those two parameters R and beta, subject to the fuzzy initial condition this, where R beta are there. So if I solve this for particular values of R beta, so I can have the solution like this, which is exactly matching with that reference. So for different values of beta 0 and 1, etc., I can have these solutions for R, and again you can change R and you can have the fuzzy solution also. So okay, those are the analytical methods. Now just I'm touching the methods and discussing one or two methods, okay, for the differential equations. So numerical methods for fuzzy differential equations, again we have developed number of methods from Euler type method, that simple Euler method that you know. We have extended that method to fuzzy differential equation. Similarly, improved Euler method, there also the same improved Euler method we have extended to fuzzy differential equation. So two types of method we have developed, max mean Euler method and average Euler method. Here also for improved Euler method, two types of method, max mean improved Euler method and average improved Euler method. So these all are you can get from the paper, published paper are there. And the third one is weighted residual methods, that is collocation and Galerkin type method. So these two I'll discuss. The third one. Sorry, before that, actually Euler method I will not discuss, but the Euler method solution I am just giving. So this is the same simple, very simple equation, dx by dt is equal to x with tilde, means fuzzy. And x tilde 0, I have see here TFN. 0.75, 1, 1.125. So this initial condition I can convert in terms of R. Okay, and for t equal to 1, I may have the exact solution, yes, solution also, x1 tr, x1 comma r. So if I solve this using our method, so these are the exact values and these are the Ma TL. Ma has already solved that. So that is why we consider that example. So these are the solutions of Ma, and this method 1, method 2 that we have developed for Euler method are given here. You see more or less they are matching with the exact solution and Ma solution. So here again we have taken H equal to 0.1. As we know that Euler method actually depends upon the H that you are taking. So in the next you see I have reduced H to 0.01. Then you see the solution, method 1 and method 2. Okay. This is in error for different values of R and H in methods 1 and 2 means if I take H 0.1 and 0.01, Then method 1, method 2, how they are comparing as we increase R from 0 to 1 for different values of R, maybe 0.2, 0.6, 0.8. You can see the solution. Similarly, we have also, I am showing that fuzzy predator-prey model. Ahmed et al. In 2012, they have solved this equation, simultaneous equations. So here the initial conditions are again TFL. So I can convert this to Arcot form. Then I have the solution like this using Euler, method 1 and method 2. And this is again for Euler taking H.1. This is for H.01, reducing the H. So these are about Euler method. So next, just I will skip this. Okay, now I will come to the third method, that is the method 5 from the weighted residual method, that is implemented from the collocation method. So let us take the linear differential equation as y double dash plus y is equal to minus t with tilde, subject to Gaussian fuzzy initial condition. So for Gaussian fuzzy initial condition like this, we have considered y tilde 0 is equal to this. So y tilde 0 I can write in terms of r like this. Y dash, y and y dash I have been given. So this problem have been solved by Bede, and he has given the solution like this: y lower TR and y upper TR. So if we use our collocation method, see we what we do in collocation method, we have to find the residual. So here residual is R, T, C0, C1, C2. So if I take 3-term solution. So if I take 3-term solution, I will have the residual like this. So if we collocate at some point T0 is equal to 0.5, T0 equal to 0.5 or half. So we get the system of equations like this, where you see C0 upper, C1 up, C0 lower, C1 lower, C2 lower, and these are the C0, C1, C2 upper values. So if we solve this, so we'll get all these lower upper. I can substitute this, and I can have the residual. We need actually C0, C1, C2 in terms of intervals. So we have suppose the solution as 3 terms, so we can substitute there and we can have the solution. So these are the solutions. So this y lower and y upper, and these are the pictorial representation of the solution. So you can see this is a TFN type 3-dimensional plot. It is time. These are the solution. This is Arcot. So using our proposed method, this is the solution. So if you see by digital values of those, bound solution for t equal to 0.01, as we vary r from 0 to 1, 0.1, 0.2, etc., how your y lower and y upper are varying depending upon different r. Okay, so similarly, we can use the Galerkin method also. Y double dash plus y plus t is equal to 0, taking this y0 and boundary value problem this we have considered. So y0 and y1 in terms of again Arcot we are given. So exact solution by Bede again in 2008 he has given y lower and y upper. So we have solved this using Galerkin method. So after using the same procedure that we know in Galerkin, but with that in that fuzzy Arcot and beta parameter. So we get this constants lower and upper like this. Again, it is a system of equations. So here you see here we don't have any fuzziness or interval here. Only different R we have. So for particular value of R, I can solve this C1 lower, C2 lower, etc. And after finding these constants, I can substitute into the assumed solution, and I can have then the approximate solution depending upon the what term solution you have taken. So these are the solution in terms of R and T. So here in table 11, I have given fuzzy solution for particular value of T, namely T is equal to 0.1, where R is the first column, different values of R, and Y lower and Y upper are given like this. This is the absolute error, and this is Y upper and Y lower. See, this is small and it is, sorry, Y lower and Y lower, this is capital. Okay. So, and this is Y, Okay, see what we have, I have given actually this y lower, y upper. These are the initial conditions. The solution I have written in terms of capital Y. Anyway, so these are the absolute error for t equal to 0.01. T has changed to 0.1 to 0.01. So now I will show just to, I will not show the solution or numerical results of this. Just I will give you an idea how to handle the fuzzy partial differential equation. So again, double parametric form we have used. This is the partial differential equation, del 2v by del s square plus 1 by s del v by del s is equal to 1 by c square del 2v by del t square. So this is actually actually vibration equation. So this equation may be written in terms of this, and then with fuzzy initial conditions I can write, means we can assume as TFN with some f, whatever f you will give, so you can have the initial conditions. So this is V dash, another initial condition. With this, so I can write the equation in terms of S and T. So finally you see STR using the single parametric form, so TR. So I have LSTR like this and the fuzzy initial condition like this. So using this I can solve, actually I am not going to into detail of this. So again, this is published paper, so you can go through that, and if you have any problem, anyone can write me by mail or ask questions. So using double parametric form, there we have T and R. So here you can see that this beta has come, this beta that controls the beta belongs to 0, 1. So this converts to interval, and interval from interval I can get the Chris values by using R. So subject to initial conditions, this again it is having beta. So R and beta are there. So again we can solve this using any method, numerical method for particular values of R and beta. Okay, so I am now showing another application problem, that is vibration analysis of uncertain beam, where we have used fuzzy finite element method. Means actually this method also we have developed, means fuzzy finite element. People have done, but we have done in our own way. So suppose this is a beam, so we just divide this beam into 3 elements, element 1, element 2 and element 3. So I have 4 nodes. Node 1, node 2, node 3, node 4. So those who know finite element, they can know that this type of element wise we divide the domain. So after discretizing this, so we can have these conditions also with I means element, 3 elements. So these are the typical beam element, node 1 and node 2. So I am not going into those finite element thing. So this we assume this displacement as Ux as cubic equation. Then we can have this Uxt in terms of those shape functions, and the kinetic and potential energy for each element I can write this Ti and Vi. Okay, so these are for ith element. Similarly for 1, 2, 3 I can put for I. Then actually finally using Lagrange equation we can convert this to this equation m u double dot plus k u is equal to 0. So where mi is this matrix and ki is this matrix, and this I are the I for the element 1, 2, 3. Where this m is called mass matrix and k is called stiffness matrix. So this equation I can convert to eigenvalue problem. So our aim, actually what we have converted this differential equation to eigenvalue problem, and from eigenvalue problem I can find the eigenvalues and then I can find the solution of this problem. So this is the eigenvalue problem, ki lab w equal to lambda mi w, where w is w1i, w2i, w3i, w4i, and lambda is omega square. So I can solve this. So if I solve for lambda, that means I can find omega, I can substitute omega here, I can have u. Okay. So I will go to the solution. So suppose I have homogeneous bar. So I have taken like this, ai and I moment of inertia, etc. length, this. So Young's modulus and densities, if I have in TFN, so you see 3 elements are there. In density also 3 elements are there. So using alpha cut, I can write this EI in terms of interval. Similarly, rho I in terms of interval. Using this, I can have the fuzzy eigenvalues for 3-element discretization of this beam. So these are, I am having the 4 eigenvalues. Lambda 1 lower, lambda 1 upper, lambda 2 lower, lambda 2 upper, like that. So for different values of alpha. Okay. Similarly up to lambda 6, lambda 5, lambda 6. So if we vary those R, I can plot also fuzzy plot for different eigenvalues. You can see this is TFN again, the solution. This first eigenvalue, second eigenvalue, then third eigenvalue, fourth eigenvalue. This is fifth, this is sixth. Okay, so with this, then I will go to another application problem. Suppose I want to solve this civil engineering problem, multi-story shear structure. So this structure actually, if you see, this is actually a 3-dimensional problem. But in generalized form, just I have taken as a single degree of freedom system means 1-dimensional problem. So have some idea of the solution. So this is actually spring mass system where each spring is having stiffness as K1 tilde, K2 tilde to Kn tilde. If I have m springs and the masses of those mass are m1 tilde, m2 tilde, mn tilde. So this is just a spring mass system. So then the Ki and Mi, I told that Ki tilde and Mi tilde are fuzzy. So these are we have taken as TFN, Ki lower, Ki center and Ki upper. Similarly, Mi tilde as Mi lower, Mi center and Mi upper. So this, after taking this, I can, we have taken both actually triangular fuzzy number and trapezoidal fuzzy number. In trapezoidal, I have 4 elements, Ki tilde, Ki this, Ki, Ki upper bracket, Ki lower bracket, like this, just a notation. So 4 elements will be there. So again, we can convert that building problem, generalized form, into again an eigenvalue problem. So if we solve this fuzzy eigenvalue problem using R and beta, etc., that I have already discussed. So using C, where K and M, I have this. These are the shapes of those stiffness and mass matrices. And you see here K1 plus K2. Actually, these are in fuzzy form. That means K1 tilde and K2 tilde is having, if it is TFN, 3 elements. So those we have to add, and you have a fuzzy matrix. Similarly, for mass also you have a fuzzy matrix. W is also a fuzzy vector. So using R and beta, so if you have alpha cut, so I can have K1 tilde alpha, K and W tilde alpha, etc. So this eigenvalue problem I can write in terms of alpha form or alpha cut form. So then K bar alpha and M bar alpha will have only the parameter as alpha. Okay. So with this, I've taken numerical example for suppose 5-story shear building. That means 5 springs. Okay. So if you use the 5 springs, so I have the 5 values of the stiffness, K1, K2, K3, K4, K5. So see, initially I have taken the crisp values. Means these are not fuzzy. And M is M1, M2, M3, M4, M5. These are also crisp. So if it is crisp, no problem. We have many softwares. A direct solution we can find also. So these are the crisp values of the crisp solution of the system when I have the crisp values of the stiffness and masses. So I have, these are the 5 eigenvalues and these are the corresponding eigenvectors. You MATLAB directly you can solve this for the crisp ones. Now if these are fuzzy, so fuzzy means stiffness and masses will be in terms of these components. So you see K1, K2, K5, these are all 3 components means TFNs. Similarly, MIs are also TFNs. So using this, so K alpha, K1 alpha, K2 alpha also I have to written in terms of alpha cut. So there are many computations. So using this and whatever that means when we convert those to the alpha form and beta form, then I can use for different alpha and beta, I can find a solution using particular values of those parameters. So I don't know whether you can see this or not. This is a very small font anyway. So these are the left bound of the frequency parameters. So I have the lambda 1 lower, left values I told. So lower one I am showing here, lambda 1 to lambda 5 and corresponding eigenvectors as we have the different alpha values from 0 to 1. So this is for lower values, left bound of the eigenvalues and corresponding eigenvectors. And these are the right bounds and corresponding eigenvectors. So special case, actually this C metal has solved a problem which was published in Journal of Sound and Vibration. So they have solved with some particular values. Those values we have taken and plugged into our problem, and we solved that to have the means confidence that our method is correct. So using those values that we have compared the solution. So these are the Kuss values. So I have, sorry, no, these are the left values, left bounds, and these are the right bounds. Okay. So if you see now the comparison, this is SIM that I told from Journal of Sound and Vibration. This is our present method, which are more or less comparable. See, because 158.86, we got 157.8. Similarly, 211, 209. You know that as we go means more or more towards the more eigenvalues, so it may means depends upon the method, problem, etc., etc. So these are more or less good matching with the C metal. So these are the natural frequency, again fuzzy plots. This is lambda 1 lower, lambda 1 upper, first frequency or first eigenvalue. This for the second, this for the third and fourth, left and right, 5. So now the mode sets, if you see, you cannot see although the distinction between center, left and right, but if you zoom this, so then you can see that there is a left one dotted line and right one dotted line in red, left one is green and middle one is blue. So these are the mode steps, means using those eigenvectors. So this is the first mode step, this is the second mode step, left side is third, right is fourth, then fifth. Okay, then these are the for particular values of alpha also I have plotted. These are so okay. So more or less I have just touched upon the problems, methods, etc. I hope you may not understand although the inside all those things. So if you can just see our papers, there the methods and details are given. You can see those and try to discuss. If you want, I can discuss also those problems. So you can develop your own methods also. And moreover, that I am not telling these methods are most efficient. No, because whatever I know that very few people have worked or working on this interval and fuzzy this type of problems. So there need to do more research on these directions to have better and efficient methods. There are many complications, many complications are there. Many you have to see those complications to how to avoid. I told already subtraction, division. We have the problems. So we are avoiding those. We have to define your computations. You have to do your computations so that you get better and better result to handle the actual practical problems. So next I'll just show a few of my related books. I have other books just related to this uncertainty and fuzzy and neural network. So this is the MATLAB means interval finite element method with MATLAB. So all these books have been more or less written with my PhD students. So this is Sukanta Nayak. Second one is actually edited book, that is Mathematics of Uncertainty Modeling in the Analysis of Engineering and Science Problems. Then so then I don't know what is happening. Okay. So this one is Concepts of Soft Computing by Springer. Again, these are to my PhD students. Then this it is very good book, Fuzzy Differential Equations and Applications for Engineers and Scientists, with two of my PhD students, published by Taylor and Francis. Then we have fuzzy arbitrary order, means see people have also are working fuzzy that fractional differential equations, that is arbitrary order differential equation. We have also introduced fuzzy arbitrary order differential equations. So though there you can have some methods and problems related to fractional differential equations are fuzzy also introduced. Again with my students we have written these books. This one again is just published by Wille. This is edited book, Mathematical Methods in Interdisciplinary Sciences. This is left one is Recent Advances in Applications of Computational Fuzzy Mathematics. Myself with some professor of Sri Lanka, we have written this, we have edited this. And this right side is neutron diffusion. again with means uncertainty with my student Sukanta Nayak. Then these two books recently, just within lockdown, this are published with my students. One is this Rajaram Mohan Jena and Subrat Jena. This one, time fractional. It is again fractional order biological systems with uncertain parameters. And the right one is affine arithmetic. Yes, this affine also people are doing recently. That also we have just touched upon. Affine arithmetic based solution of uncertain static and dynamic problems with my student Saudamini Raut. So this is one journal that I am the editor-in-chief, that is International Journal of Fuzzy Computation and Modeling. You can send your paper related to fuzzy and uncertainty. So we have good means advisors there, editors. You can send your paper for possible publication. So this is my group, although there are a few more new have joined. Those are not included till now. So I have three groups. One is ANN, fuzzy ANN, and interval ANN. Another group is vibration and fluid. And other one is fuzzy or interval, affine or fractional. So these are my all students group with me. Many of them have already completed PhD. Few of them are working, and new one already I told that I have not included till now. So with this, if you have any question, simple question, so you can ask me. So
Thank you,
thank you.
professors, for thought-provoking talk. And now I open this session to the audience for questions and discussion. Okay, so I have one question from live session, sir.
Yes.
From Dr. Namrata Rana Rao is how to know which types of fuzzy number will fit for which type of problem, as there are different types of fuzzy number.
Yes. So actually, we are mathematician. I am mathematician. Okay, so that is not my work that which practical problem will fit for which membership function. That should be given by the user, engineers or other scientists, those who are having. Suppose I want to solve the building problem. So this is actually civil engineering problem. Here Young's modulus or density or moment of inertia, how it is behaving, whether it is behaving with respect to interval type or TFN or tank. That is why if you see in my problem, sometimes I have taken TFN, sometimes TRFN, sometimes Gaussian. See, our work is to give the general method, and then as per the need, you can use those whatever fuzzy. It is correct that that is a good question. But see, we have given the model. You can use your own membership function and you can solve. Okay.
Okay, Professor, he has one problem along this problem. Can we take membership values other than 0, 1 like reciprocated lattice or postulated sets?
Till now, actually, it should be closed bounded set. Actually,
Yes, sir.
okay. So till now, yes, I don't know. Means I have not done in that direction. Yeah, it should be piecewise continuous. Those conditions, if it is satisfied, then you can take. Okay.
So,
I can see some other question as well. So can you also ask? Like calculation in fuzzy differential equation is very lengthy. Can you use any software or calculation or just use any other methods to solve this question? So
Yeah, till now, no software is available. Interval, some software is available in lab. Okay. That also we have tried, but we could not succeed to use that. We have written our own computer program and all. Till now, no direct software is available actually for fuzzy. For fuzzy logic, you have in that MATLAB. People are using that if then and those rules. There you may have the software. You have some softwares, but not like this using those uncertainty in the civil engineering, electrical engineering, or other practical problems. Till now, to the best of my knowledge, you don't have. Okay?
And another question from the Dr. Dhanasekaran. What
Yes.
is beta in the interval form?
Beta is the second parameter that I am using. Uh, Beta alpha is alpha cut. Okay, when I have a TFN, so I have three elements A, B, C. So if I want
Mhm.
to convert to the interval, I use alpha, and from alpha, if I want to convert, actually it is not crisp, but if I say suppose roughly it is crisp, so I have to use beta. So now giving different values of alpha and beta, you can have the solution whether you want means the crisp solution, interval solution, or fuzzy solution. Okay, if you want to in
Mhm.
detail, you can go through in any of my differential equation paper, so you can understand what is that beta. Okay.
And another
Yes.
question from the Anupam. Whether W is weight or anything else in fuzzy eigenvalues.
W, okay, AX equal to what W? Where W, where you got?
He's
W?
asking that whether W is Anupam. Can you hear me? You can ask directly to our speaker.
Yeah, which W is he or she is referring? Means it is
I don't
AX
know.
equal to lambda,
He
lambda
has
BX?
written in the chat box whether W is weight or anything else in fuzzy eigenvalues.
See, for eigenvalue, you know AX equal to lambda BX or lambda X. So she
Mm-hmm.
is telling lambda equal to omega, that is W. I don't know. I could not understand.
Maybe
W is not
maybe
weight.
he.
In eigenvalue problem, W is certainly not weight.
Mm-hmm.
Okay.
And another question from an participant. Please mention some importance of fuzzy set in ordinary differential equations.
Importance.
Exactly.
So
Yeah.
I already told that whatever problem you take, see, whatever problem we take till now, we are solving what? We using CRISP. But in general, suppose I want to measure anything. So whether we will have uncertainty. So in
Mm-hmm.
actual case, in your all models, you have the uncertainty. Okay, so those uncertainty need to be solved using uncertain methods, fuzzy or stochastic or interval. I already told that stochastic when to take and interval and fuzzy when to take. Hmm?
Mm-hmm. And the last question from an participant, how to handle variable as a fuzzy in differential equations?
Those are methods are there, but that is a good question. Till now, people have not done much work on this. That is a good question. Another challenge is that if you have 4 5 parameters, 2 are fuzzy and 3 are stochastic, random. So how to combine those? Okay, so that is a good
Mm-hmm.
question. Okay.
And another question from the same participants, give an example where we use double parametric form.
I have already given example that building problem, double parametric form I have used here.
Mhm. Okay, so thank you for the
Okay.
discussion.
Okay, Professor. Thank you
Yes,
once
thank you.
again for taking time from your busy schedule and
Thank
deliver
you.
a nice lectures in our workshop. Thank
Thank
you
you.
so much, sir.
Thank you. I appreciate and thank you very much. So I hope you have these workshops a great success with various well-known means other. I have seen the series of persons that they are giving the lecture. So anyway, thank you very much.
Thank you, sir. Thank you for.
Okay. Okay.
Okay,
So now
now it's over to Dr. Anand to introduce our second speaker.
okay. So can I close my session? Means I can.
Yes, sir. Yes, sir.
Okay. Okay. Thank you because I have another meeting. That is okay.
Okay, sir.
Okay.
Thank you, sir.
Thank you,
Okay.
sir.
Once
Thank you.
again.
Thank you. Thank you very much.
So thank you, Mahesh. As we have seen in the last lecture, Professor Chakravarti discussed about the basic fuzzy sets and how to handle the uncertainty present in the real life via modeling problem from the fracture mechanics using the fuzzy differential equations. So in this continuation, the second lecture for today's session will be focused on how these techniques can be applied in solving some specific type of differential and difference equation. So let me now introduce our second speaker of the today's session, Professor Ali Raja Khastan. He obtained his master's and PhD in applied mathematics at the University of Tabriz in Iran. Having done his PhD degree, he visited the Santiago de Compostela University in Spain for the further research, after which he joined Institute of Advanced Studies in basic sciences, where he's currently working as an associate professor at the Department of Mathematics. He is author and co-author of more than 5 research papers. He is a board member of the journal Fuzzy System. His research activities are devoted to the study of the properties of solutions of nonlinear problems, and several of his works are focused on the topic of fuzzy differential equations as a tool to handle the uncertainty present in many phenomena. So now it's over to Professor. So, sir, please.
Thank you. First, is it okay? The slide.
Yeah,
Yes, sir.
can you go to yeah? Okay.
Okay. Thank you, Professor Anand. First, I would like to thank to the organizer of the workshop for organizing this event, and also the invitation and giving this opportunity to me to present some of our results. My voice is okay?
Yes, yes.
Okay.
Your voice is clear.
Okay, so most of the results that I'm going to talk about it today are done jointly by some colleagues from Spain, University of Santiago de Compostela, and some colleagues in Turkey and Czech Republic, Professor Irina Perfilieva, and also some of my students in Iran. The title of my talk is Some Results on Fuzzy Differential and Difference Equations. Actually, after the nice talk of the Professor Chakravarti, it is not easy task to talk on fuzzy differential equation. He is one of the leaders on fuzzy differential equation and also other topics, as you listen to his talk. But on the other hand, it is easier for me now to talk on fuzzy differential equation because some of the preliminary, some of the basic definitions are same with previous talk. So I will skip the preliminaries. Actually, this talk is prepared and bring some result. In most of them, I did not include the result of the Professor Chakravarti, supposing that he will talk about his results. So I will start my presentation about our results. So the outline of the lecture is about, the first is the introduction of fuzzy numbers and fuzzy derivative, later considering the fuzzy differential equations in different approaches and different formulations of first order fuzzy linear differential equation, and then introducing the fuzzy difference equation, and finally one new topic in fuzzy mathematics and interval mathematics, interval fractional difference equation, and finally the conclusion part. I start by the definition of fuzzy numbers. As we saw in the previous talk, we had the definition of fuzzy numbers, so I just escaped this part. And so we show the space of fuzzy numbers by RF, and we call it the fuzzy number space. The type of fuzzy numbers that we use normally in our works are the LR type fuzzy numbers. That the definition is given here. So I just escape the definition. And in a special case, the trapezoidal fuzzy numbers and triangular fuzzy numbers and the RS fuzzy numbers, these are special cases of the LR fuzzy numbers that we will use in this talk also. For the addition and scalar multiplication of fuzzy numbers based on the Zad extension principle. Sorry, just based on the fuzzy Zade extension principle, we can define the addition and scalar multiplication of fuzzy number using the interval mathematics. So here, if u and v are fuzzy numbers and lambda is scalar, so the alpha cuts of u plus 1 is equal to addition of alpha cuts of u and v. Similarly, for the scalar multiplication lambda u, it's lambda multiplied by alpha cuts of u. Here we use the interval mathematics, the addition of two interval and scalar multiplication of intervals. So the addition and scalar multiplication for fuzzy numbers is based on the interval mathematics that we use here. There's one theorem which is very important for us in our result, and that the addition of fuzzy number is associated and commutative, as you see here in this the first equation, and the singleton fuzzy set is the neutral element with respect to addition. That means we have this relation, and none of the fuzzy numbers in this space has an opposite in RF with respect to the addition. And another important property, for any A and B in R with this property, A, B is positive, greater than 0, greater or equal to 0, and any arbitrary fuzzy number, we have this relation, we have this equation, and generally we don't have this relation. Only for the A and B that satisfy in this equation, we can write this equation. And also the last property that you see here, this is very similar to the classical mathematics. So using the property 3 and 4, we see that the space of fuzzy numbers is not a linear space. So when it's not linear space, so we cannot consider it as a normal space. And so we have some difficulties in studying the space of fuzzy numbers because it is not a linear space. Also, the product of fuzzy number, as you saw in the previous talk, is defined by this relation, and it's the optimization problem that we need to solve for any alpha to obtain the multiplication of two fuzzy numbers. And the other important topic in the fuzzy differential equation is the definition of difference, mainly the Hukkara difference. Let u and v be fuzzy numbers. If there exists w as a fuzzy number such that we have this equation u equals to v plus w, then w is called the H difference or Hukkara difference of u and v, and it's denoted u minus v, and we have this equation u minus v equals to w if and only if u equals to v plus w. So generally, the Hukkara difference of two fuzzy numbers does not exist. If there exists such a fuzzy number that we have this equation, it exists. And the important property, when we consider the Hukkara difference, u minus u for any fuzzy number is 0. But when we consider the standard difference, that means u plus minus 1 multiplied by u, this is not 0. And another, so the Hukkara difference rarely exists, and in many cases we don't have the Hukkara difference of two fuzzy numbers. So several alternatives are proposed for the generalization of fuzzy difference of fuzzy numbers. For example, generalized Hukkara difference. Okay, now the generalized Hukkara difference of fuzzy numbers for given two fuzzy numbers u and v, and the generalized Hukkara difference or shortly GH difference, is the fuzzy number W if it exists such that we have this relation U minus GH difference, U minus V equals to W if one of these two relation holds. And to obtain the alpha cuts of GH difference, we have this proposition, we have this relation. So we can obtain the alpha cuts of fuzzy numbers by this relation. And for the first time, this definition, the definition of GH difference is introduced by Stefanini in 2010. Another topic which is very important for us is the metric structure of the fuzzy numbers. The metric structure in fuzzy numbers is given by the Hausdorff distance, that we show it by D, or sometimes we show it by D infinity. Which is, and the definition is like this relation, and it has some important properties. The first one, as you see here, the second one, and the third one. And the last one, that it is very important for us, that the space of fuzzy numbers with this metric is a complete metric space. So we will use this result in the fuzzy differential equation, since by this property we can use the Banach fixed point theorem to study the existence and uniqueness of the equation, fuzzy differential equation or fuzzy integral equations in the space of fuzzy numbers. To study the fuzzy differential equation, we need a definition of fuzzy derivative, and this derivative is based on the definition of fuzzy difference, and here we use the Hukara difference. So let f be a fuzzy number, be a fuzzy function. We see that f is Hukara differentiable, or shortly H differentiable at t0 if there exists an element f prime t0 such that the limit, both of the limit exist and are equal to f prime. So to define the fuzzy derivative, both of these H difference for any H near to 0 need to be exist. So now we are in a position that we can study we can introduce the fuzzy differential equation in the, let us consider the first order fuzzy differential equation with initial condition, the Cauchy problem, y prime t equals to f and y t0 is y0. We consider this as a fuzzy differential equation. Why? What is fuzzy here? When y0 is a fuzzy number, when we consider y0 as a fuzzy number, so then the y as a function need to be a fuzzy function, fuzzy number valued function. And when y is a fuzzy function, so the definition of the derivative for this function should be a fuzzy derivative. So we use here the Hukara derivative. So generally we have a fuzzy differential equation with fuzzy initial value and fuzzy derivative and fuzzy functions. Sufficient condition for the existence of the unique solution for fuzzy first order fuzzy differential equation is similar to the classical case, and the condition are continuity and Lipschitz condition for the f in second variable. And fuzzy differential equation under Hukara derivative is studied in many papers and books. And for the first time, Kaleva in 1987 studied the existence and uniqueness of the solution for first order fuzzy differential equation. And later many researchers studied the numerical solution of the fuzzy differential equation by Taylor method, multi-step method, and fuzzy transform, and other methods. Some good reference to study the fuzzy differential equations especially with the Hukara derivative. The first one is in 2003 by Professor Lakshmikantam, Theory of Fuzzy Differential Equations and Inclusions. The second book are the Mathematics of Fuzzy Sets and Fuzzy Logic by Professor Bede. And the third one is the book by Professor Gomez and Barros from Brazil and Professor Bede also, Fuzzy Differential Equations in Various Approaches. And the last one, which is the most new here by Professor Chakravarti, is a fuzzy differential equation and application for engineers and scientists that we saw in the previous talk. Different approach to study fuzzy differential equation. As Professor Chakravarti said in previous talk, we have different approach to study the fuzzy differential equation. One of them is to use the alpha cuts, translating fuzzy differential equation to a system of ordinary differential equations, and use the numerical methods to study the fuzzy differential equation numerically, and there are many results on this topic. The another approach to study the fuzzy differential equation is that the colleagues from Turkey, from the Ankara University, they consider fuzzy differential equation as a crisp differential equation with fuzzy initial condition. And they propose the solution as a bunch of crisp solution as a fuzzy set. So they split the fuzzy initial value problem to a non-homogeneous crisp problem and a homogeneous problem with fuzzy initial values, and they solve both of these problems and to obtain the fuzzy solution. Another approach to study fuzzy differential equation, which is done by Professor Barros and his colleagues in Brazil. First, they fuzzified the derivative operator using the Zad extension principle. And after they applied to study the fuzzy differential equations. So they fuzzified the derivative operator and obtain a new definition for fuzzy derivative, and they use it for the fuzzy differential equation. The another approach to study the fuzzy differential equation is using differential inclusion, which is done for first time by Professor Hullermeyer in 1999. We will talk about the first approach, I mean using the alpha cuts here. So let f be a fuzzy number, and having these alpha cuts for each alpha, if f is Hukara differentiable, then f alpha and g alpha are differentiable functions, and we have this relation for the alpha cuts of the derivative of f. So by this property, we may replace fuzzy initial value problem by the equivalent ODE system, this system, which is now an ODE system, or in the parametric form, which is given by this system. So we transfer fuzzy differential equation to a system of ODEs system, and then we can use an analytical or numerical method to solve this ODE system. So some of the researchers have solved the equivalent parametric ODE system to obtain a numerical result for fuzzy differential equation. Also, in one of the work jointly by Professor Prefilieva, we used fuzzy transform to obtain the numerical solution. Now, some properties for the Hukara differentiable fuzzy functions. A Hukara differentiable function, fuzzy function, has a non-decreasing length of the support. That means when time goes by, the diameter of the fuzzy solution is increasing, that we will see in the examples. If f is Hukara differentiable, then it is continuous, and we have the last property pretty last equation for the addition and scalar multiplication of, for the derivative of these relations. So if f and g are fuzzy differentiable functions, then we have these relations. Another property, when is f is a continuous fuzzy function, for all t, the integral g is differentiable, and we have this relation. Also, the second one, let f be a fuzzy differentiable, Hookery differentiable, and assume that the derivative f prime is integrable over I. Then for each s, we have the following in the following equality. The last property, when c is a fuzzy number and g is a real valued function from a, b to a positive real numbers, and it is differentiable on x naught with g prime and x naught negative, then this simple function fx is c multiplied by gx, which is a multiplication of a fuzzy number in a real valued function. This function is not Hookery differentiable. So in 2005, Bede and Gall, they tried to define a new definition for derivative of fuzzy number to enlarge the class of fuzzy differentiable functions as a generalized Hookery differentiability or strongly generalized Hookery differentiability. Let f be a fuzzy function and fix t naught in I. We say that f is one differentiable at t0 if there exists an element f prime such that for all h sufficiently near to 0, there exists this h difference and the limits in the metric d. So for the one differentiability, we need to guarantee the existence of these two h differences and also the existence of this f prime as a fuzzy numbers. In this case, we denote it by d1, 1. That means the first derivative, and in the first case, one differentiable. Similarly, we have two differentiability here, such that the h difference are different. You see here and here, the h difference are different, and so the limits also are different. If this case satisfied, then we call it f is two differentiable and we note it by this notation. We have this result for the strongly generalized differentiability. The first case is the Hookery differentiability, so we had it before. When f is fuzzy function having this alpha cuts, f is one differentiable, then f alpha and g alpha are differentiable functions, and we have this relation. If is two differentiable, then f alpha and g alpha are differentiable function, and we have the second equation. But we see that the position of the f alpha and g alpha, they change here for the one differentiability and two differentiability. And we have some properties, some well-known results for the generalized Hookery differentiability. For example, for the in the first case, if f and g are generalized differentiable at t in this same case of differentiability, then f plus g is generally differentiable, and we have this. So generally, this property does not hold for different cases of the differentiability. When, and the next theorem, when f is one differentiable and g is two differentiable, or f is two differentiable and g is one differentiable on an interval, if the h difference exists for t in this interval, then f minus g, the h difference, is generalized Hookery differentiable, and we have this relation. We need these two conditions in the next result. We say that if satisfy the condition h1 at t, if it satisfied, if these two h difference exist for h sufficiently small, And similarly for the H2, we have this H difference. As we see, this is for the existence of one differentiability, because the diameter of the solution, diameter of the fuzzy function here is increasing, and here the diameter of the fuzzy function is decreasing. So the first case is for the existence of the one differentiable function, and the second one is for the two differentiability. So the result. Let f be a fuzzy function, let f be a real valued function and g be a fuzzy valued function, both of them differentiable. If f prime is positive and g is one differentiable, then fg is one differentiable, and we have this relation. Similarly for the two differentiability, when f prime is negative, we have the same result. In the third case, when f prime is positive and g is two differentiable, and if fg satisfy condition h1 at t, then fg is one differentiable, and we have this relation, which is different from the previous ones. So for the derivative of the multiplication of two functions, see we have different results. Again, we can obtain the similar result depend on the type of the differentiability of G and also the condition H2 or H1. We have similar results. So now, using the previous theorem, we can study the first order fuzzy linear differential equation. Here,
1 comma e. Okay? And this is just m. For same reason, this is also commutative, and this is also.
Sorry for the inconvenience. Now you can.
Okay. To consider the first order fuzzy differential equation, linear differential equation, here we consider this problem, which is very similar to the classical case. But here, y naught is a fuzzy number, a is a real valued function, and b is a fuzzy function, fuzzy number valued function, and both of the a and b are continuous. To study this problem, we need to define two types of the solution, one solution and two solutions, depend on the type of the differentiability that the solution satisfy. We have the one solution and two solutions. So let y be a fuzzy function such that the first derivative and the d1 and d2, that means the one differentiability or the two differentiability of the f exists. If y and the one differentiability satisfy problem 2, we say that it is one solution. Similarly, if y and derivative of y in second case in two differentiability satisfy problem 2, we say that y is a two solution of problem 2. To study this problem, we consider it in three different cases: when a is negative, a is positive, and when a equals to 0, which is done by Professor Nieto and Professor Rosana Rodriguez Lopez from the Santiago de Compostela University. The first case, when a is negative, the one solution of problem 2 is given by this equation. This is the solution, one differentiable solution, and this is the second equation is the two differentiable solution for the first order fuzzy differential equation, provided that the h difference in both of the case exists. For the positive a, we have a similar result. When a is positive, the two solution is given by this equation, and one solution is given by this equation, provided that this h difference exists. And this is the one solution for the problem 2 when a is positive. For a equals to 0, we have the problem reduced to this problem, and here we have one solution like this and two solution like this. So we see that here we have the age difference, and provided that this age difference exists, we can have two different solutions for first order fuzzy differential equation. As an example, we can consider this first order fuzzy differential equation here. Gamma here is a triangular fuzzy number that we have the alpha cuts, and the initial condition also is a gamma. According to the previous theorem, here the A is negative, so the one solution is given by this equation and the two solution is given by this equation. We see that the two solution is given by this equation, but provided that this age difference exists, which exists only on the interval 0 and 1. So we have two solution on interval 0 and 1. Can see in the figure. So this is the one solution of the problem. So you see that here the diameter is increasing, the fuzziness is increasing, and this is the two differentiable solution. Here the diameter is decreasing. So we have two different solutions for first order fuzzy differential equation, depend on the derivative that we use. Also, we can study the fuzzy boundary value problems like this equation. This problem for first time is studied by Professor Oregon and Lakshmikantam and Nieto in 2003, and later Professor Bede has a result that this result, the problem 3, has no solution at all under the Hooker differentiability for gamma 0 and gamma 1, such that we have this relation, and if having at least one non-real value, fuzzy value. So here, again, here gamma 0 and gamma 1 are fuzzy numbers. Here y is a fuzzy function, y prime is a fuzzy function, and y prime here is a fuzzy derivative. Here also the second order fuzzy derivative. To study this problem, first we define the definition of the solution, which is similar to the first order. If it is satisfying the problem and it is differentiable, so we call it the solution, NM solution. If it is n for the first derivative and m is for the second derivative. If, for example, it is a 1-2 differentiable, that means the first derivative is 1 differentiability and the second derivative is 2 differentiability. We call it 1-2 differentiable. So generally, we have the NM solution for the NM differentiable functions. And here also we define this solution, the generalized solution to the boundary value problem. We say y is a fuzzy function and t0 is a real value in this interval, such that y0 is gamma 0, y is the nm solution to the equation. On this interval, in the first interval, it is nm solution, and in the second interval, it is n prime differentiable solution. So we call it the generalized solution. This paper is a joint work by Nieto in 2010. So as an example, if you consider this fuzzy boundary value problem, where gamma is a triangular fuzzy number by these alpha cuts, and we have this relation. If we solve this problem, we can obtain the alpha cuts of the solution like this, which is 1-1 solution on this interval and 2-2 solution in the another interval, and 2-2 solution on this interval. So in the figure, we can see that this is the problem. This is the solution of the boundary value problem. Here the boundary 0, and here for the boundary at 1. So this is the solution of the fuzzy boundary value problem, and this is the figure. And here also, this is this is the formulation of the solution, which is 1 2 differentiable for on this interval and 2 1 differentiable on this interval. So we have the solution on the interval 0 and 1, and we call it the generalized solution for boundary value problem. And this is the solution. Another topic in the studying fuzzy differential equation is different formulation of the differential equation. For example, if we consider the first order differential equation in classical case in crisp mathematics, there is no difference between problem 4 and 5 and 6. They are equivalent, but in the fuzzy mathematics, they are totally different. So for example, if you consider fuzzy initial value problem 4, where y0 is a fuzzy number, a and b are continuous functions, this problem is not
Hello, it seems there is some technical issue with the speaker. So I'm already in touch with him. So I will update you just in a second. Uh, Dear participants, I have just worked with the speaker. So he said that he don't know there is some technical issue. So he's joining us soon.
So
Can you hear me now?
Yes, sir. Yes, sir. Yes, sir.
Okay,
Now.
sorry. And can you
Okay.
see also the slides presentation?
So just share your
sir.
side, sir.
So may I continue?
Yes, sure, sure. Just share your presentation and then you can continue. Yes, perfect. So now you can continue, please. Can you please unmute yourself? Hello.
Yes, okay. I'm sorry for inconvenience. So, and I was talking that we have different formulation for a crisp differential equation. And now everything's okay? My voice and the slide?
Yes, sir. Audible, sir.
Okay, okay, okay. So, and so generally problems 4, 5, 6, and 7 are not equivalent in the fuzzy differential equation in fuzzy mathematics. So we have different solutions with different properties for these problems, that which is these results are given in this paper jointly with Rosana Rodriguez Lopez, that I didn't bring it here. And the next topic is studying the fuzzy difference equation. The fuzzy difference equation, one of the approach is to use the generalized division. So in this, which is given by the Stefanini in 2010, let A and B fuzzy numbers having alpha cuts A and B like this. The G division is the operation that calculates the fuzzy number C having alpha cuts C underline and C overline defined by this relation. So we have two cases, the first case and second case, provided that the result, the C is a fuzzy number. Here we use also the alpha, the inverse of the alpha cut by using this equation. So fuzzy difference equation is a difference equation where parameters and initial values are fuzzy numbers and its solution are sequence of fuzzy numbers. And fuzzy difference equation are suitable in finance problem, time series, and genetic problems, and many other applications. For the first time, Lakshmikant and Vatsala, they proposed the concept of fuzzy difference equation, and they obtained a comparison theorem for the fuzzy difference equation in terms of ordinary difference equations in this paper. Several researchers, several people have worked on the fuzzy difference equation. For example, in the first paper, the authors considered this fuzzy difference equation, and when A is a fuzzy number and M is in this set. So later, Zhang and the colleagues considered the first order fuzzy Riccati difference equation, and they obtained the solution. They present the existence, boundedness, and asymptotic behavior of the positive solution. And recently, with one of my students, we proposed the solution of the first order rational fuzzy difference equation, this, then A and B are positive fuzzy numbers. Also, another work in fuzzy difference equation is the paper of Deba and Corwin in 1996. They consider the fuzzy difference, the linear fuzzy difference equation, giving the frequency of the genotype on the n+1 generation when the initial value is a fuzzy number. Here, xn is a sequence of positive fuzzy numbers, and w, q, and x0 are positive fuzzy numbers. they use the Zad extension principle to obtain the fuzzy solution. But now we consider this equation in two different formulation, two different equivalent formulation to obtain the different solutions. We use the definition of G division, generalized division, and also the standard interval arithmetic. So we have this theorem. We consider this equation in two different formulation, 8.1 and 8.2. Consider equation 8.1 where W, Q, and X naught are positive fuzzy numbers. If you have this relation, then the unique positive solution, then the unique positive solution of equation 8.1 is given by this equation, by this relation. This paper also is published in 2016. And for the other problem, A2, we consider the problem A2 where W, Q, and X naught are positive fuzzy numbers. Under this condition, again, the unique positive solution of this equation is given by this relation when we have this definition for the mu. Also, we consider the equilibrium point of both of the equation 8.1 and 8.2. I think since I don't have enough time, I escape this result. For the 8.1, we have the result here. Similarly, for the 8.2, we have this result for the equilibrium point, and the result for the boundedness and persistence of the solution. A sequence of positive fuzzy numbers is bounded and persists if there exist positive real numbers m and n, such that we have this relation. So let WQ are positive fuzzy numbers such that the W naught over line is less than 1. Under this condition, every positive solution of 8.1 and 8.2 are bounded and persist. So as an example, if you consider the problem 8.1 with the initial value x naught as this fuzzy number value, fuzzy number, and q and w also. So by the previous theorems, we can obtain the unique positive solution and the boundedness and also the persistence of the solution that we can see in these figures. For the 8.1, this is the solution, and for the 8.2, this is the solution. And the last part of the topic is new in the area of the interval differential equation and differential equation also in the fuzzy. Here we present the new concept of interval discrete fractional calculus. Interval and fuzzy fractional calculus and fuzzy differential equation are studied in many literature recently, especially in the last decade. And so here we consider the discrete case, so as an interval discrete fractional calculus. So let f be a real value. Let f be a interval valued function such that we have this for the lower and upper branch of the f, and it is a sub-interval of R. Then f is said to be w increasing. We say f is w increasing or w decreasing, respectively, if the real valued function length is increasing or decreasing, respectively. So the properties w increasing or w decreasing depends on the length of the function. Now forward and backward difference operators. Let f be a interval valued function where the domain in A is defined here. The first order forward and backward difference of f is defined respectively by this relation. which is similar to the classical case, but we have here the GH difference. This is for the forward difference operator, and this is for the backward difference operator, delta and nabla. Using the GH difference, we can define the higher order difference operator, forward and backward, by these relations. And we use this concept, the factorial function or generalized falling function in our result. We define T nu by this relation, provided that the right hand side is well defined. So as a definition for the fractional sum, it is like a discretization of the fractional integral. Let f be interval valued function and nu be a positive number, then nu order fractional sum of f is given by this equation. So this is the fractional sum of order nu. And we have the trivial case, we define it like this. And here S is like S plus 1, the forward jump operator. The fractional difference operator. So let f be a interval valued function and nu is a positive number. So n and also n be a natural number, is such that we have this equation. We can define the Riemann-Liouville fractional difference of f for this interval valued function by this equation. So it is very similar to the Riemann-Liouville fractional operator in a continuous case. We have the composition rules for the fractional sum for the function f and nu and mu. We have this relation for the composition rules, and we show the first order difference when we have the first kind of the difference in the GH difference. We show it by delta 1. It is like this, and we have when we have the second case of the GH difference, we have this relation for the difference operator. We will use the delta 1 and delta 2 in next result. Let f be an interval valued function and nu in this interval. If f is w increasing, then we have this equation, which is important to study the interval discrete, fractional discrete interval fractional difference equations. And also when w is decreasing and satisfying the condition 9, we have this equation, this relation. Also, we may unify both of the equation in the previous result. In this equation, we demonstrate that using the definition of GH difference, we can write this equation, provided that f is either w increasing or w decreasing and satisfy 9. So we have this relation, which is important to study the interval fractional difference equations. And also we have two other results. When f is w increasing, we have this equation, and when f is w decreasing and satisfying 9, we have this relation. So to study the interval fraction difference equation, this result are done by one of my PhD students, by Rana Bek Mohammadi. Is working on interval fractional difference equation. We have submitted it. The paper is appeared in the Iranian Journal of Fuzzy System recently. So consider the following interval fractional difference equation with an initial condition. Here a naught is a initial condition and nu is a real value, considering the f on this relation, and a naught is an interval So in this paper, we have studied the existence and form of the solution for this problem. So as a conclusion, in the modeling of the real world phenomena, often most of the information may be uncertain. In such situation involving uncertainties, fuzzy differential equations and fuzzy difference equation are natural ways to model dynamical systems. Depending on the different formulation of the unique crisp equation, we may get different results through fuzzification. This fact is found an advantage by some researchers due to the existence of several choices with different behavior, adding richness to the theory of fuzzy differential equation and fuzzy difference equations. As a suggestion to study fuzzy differential equation, we can use the result of set differential equations and also the interval differential equation, use that result to study fuzzy differential equation. One of the work is done by my colleagues. Relation between the Bedegal or general differentiable set valued function and their associated support functions. And also studying the fuzzy partial differential equation using the fuzzy partial derivative and using the generalized Hooker differentiable. Also, we have studied the Gauss partial differential equation in fuzzy concept in this paper. Also, many papers, many results are done in the fuzzy fractional differential equations. Also, as you saw in the previous talk by Professor Chakravarti, the book he present, it is on the fuzzy fractional differential equation. So there are many areas to work on fuzzy differential equations in different fuzzy boundary value problem, periodic boundary value problem, or in the fuzzy fractional, and also in the discrete case, which is very new topic in this area. Here are some references. And thank you. If you have any question, here is my email. Thank you.
So thank you, Professor Khasdan, for your nice and interesting talk. So now I open this session for the question and discussion. So from the participant side, if you have any questions, so you can ask directly to our speaker.
I can read the questions here in the text. If it is okay, I can read and reply them. Is it okay?
So I can see some questions in the chat box as well.
Yeah.
So from Dr. Dhanesh Karan, he is asking that differentiable and differentiable formulas are only possibilities. I don't know what. And another question is, all theories and properties or theorems of fuzzy ODs are holds for fuzzy fractional differential equations as well.
All theories and properties theorem. Not always. It depends. Sometimes, for example, we can use the Banach fixed point theorem to study the fuzzy differential equations or fuzzy partial differential equation, but depends on the structure of the fuzzy number space, because as you see, it is not linear space. We have some difficulties, and the main problem on the fuzzy mathematics is to guarantee that the solution is a fuzzy function. Now, it is possible to use the classical methods to study the fuzzy differential equation, but the main issue is to guarantee that the solution is a fuzzy function.
And hello. Okay. And there is another question: how to handle a differential equation if any parameter is a fuzzy random variable?
There are some works to study the fuzzy random differential equations. That means to study the randomness and the fuzziness in same time in differential equations. I think this is the way to study that.
Okay. Anything else from any participants? So, if not, so let me thank you again, Dr. Khastan, that he joined us and he gave a really a nice presentation and talk. So, thank you, Professor Khastan, for your talk. And let me remind you that tomorrow's session is going to be. Is there any questions from Vivek?
Yes, sir. From the audience, question asking that, please suggest any good book for the fuzzy fractional differential equation for analysis, sir.
Okay. I mentioned 4 books in the slides. The first one is by the Lakshmikantam in 2003, which is only for the Hooker differentiability. But you know, in the fuzzy mathematics, the the rate of the publication is very fast, so you need to study the recent works. So the other books by Professor Chakravarti and the book by the Professor Barros from Brazil and the Professor Bede, they are really very interesting books, very good books to start and to study, with many recent works to study the fuzzy differential equation.
And the last question, sir, from audience, may explain any one application problem? So,
in the previous talk, Professor Chakravarti mentioned several applications for fuzzy differential equations. We can consider them, and also another thing that since normally we have the uncertainty in real world phenomena that we model it by differential equation. When we have uncertainty in the initial value, or when we have the uncertainty on the parameters on the function, so we need to study this uncertainty. One of the ways to study uncertainty is to study by fuzzy. So it is one way to study the fuzziness in all the ODEs and PDEs.
Okay, so
thank you very much, sir.
Welcome.
And let me remind you that tomorrow's session is gonna be very interesting. And in the first talk, we will have a speaker, Professor Alexander Sostak from the University of Latvia, and he will be discussing about the theoretical discussion about the fuzzy mathematical morphology. And in the next talk, we have a speaker from IIT Indore, Professor Muhammad Akil Khan, and he will discuss about the rough set and model logic. So I hope you will enjoy the tomorrow session as well. So that's all for today.
As a last comment,
Yeah,
thank you for all the participants. Thank you also for the organizers of this workshop. My email is hastan@iasps or gmail.com. So for any question, for any idea, for any for any collaborative, you can contact me by email. Thank you very much.
So thank you all who joined us for the really nice session. So that's all for today. So let us meet tomorrow at the scheduled time. So I ask participants now you can leave this meeting. Thank you. Thank you everyone.